Today, we're going to be talking about graphs and trees. So let's get started. What exactly is a graph? Well, a graph is a collection of two things. And these are what those two things are. It's a collection of vertices and edges. Okay, sometimes you might see vertices called as nodes. I will use them interchangeably, and most people use them interchangeably. Okay, so let's go ahead and draw an example of a graph. Okay, so here's an example of a graph. So as you can see, we have different vertices and we have edges between the vertices. So let's just give these vertices a name. So I'm going to call them 1, 2, 3, 4, 5, and 6. I don't have to call them numbers per se. I could call them letters, or I could, just give them other names. But for this example, we'll use a number. All right, so as we can see, in a graph, between the vertices, there might be an edge. So this graph here, like we can see that there is an edge between 1 and 2, and there's an edge between 2 and 1. So there's not like a particular direction. It's not like only from 1 to 2 there's an edge, or only from 2 to 1 there's an edge. This is our pretty much our standard example here. This is an example of an undirected graph. That is because if we consider the edges, there's not an actual direction. Now, I'm going to quickly draw an example of a directed graph so you can just see some contrast. Okay. All right, so this is an example of a directed graph. As we can see, there is a specific direction to the vertices, or there's a specific direction to the edges between the vertices. Okay, so this is a directed graph. If we want in a directed graph, we might have an edge going from one vertex to the other and the other way. So you might have like two edges. Okay. Yeah, so we have undirected graphs, we have directed graphs. Now there's like different ways in which we could represent the graphs. So let's go ahead and maybe let's just start with this directed graph example. So I'm going to just create a matrix. Okay, imagine that this is 1, 2, 3, 4. That this up here is also 1, 2, 3, 4. Okay. So here's how we fill this out, right? So for example, when we're looking at this row and this column, that means we're asking ourselves this question: is there an edge between 1 and 2? Well, yeah, there is an edge between 1 and 2, so I'm just going to mark this with a 1. Okay, there's also an edge between 1 and 3, and there's not an edge between 1 and 1. Like, there's not an edge between 1 and itself, and then there's not an edge between 1 and 4. Okay, now let's look at 2. There are no edges going out of 2, so this row is all zeros. Okay, let's look at 3. There's an edge going from 3 to 1, and that's it. Okay, let's look at 4. There's an edge going from 4 to 2, and then that's it. So pretty much we can represent this graph right here with this matrix. And this matrix has a special name to it. It's called the adjacency matrix. Okay, now there's another very popular representation for graphs as well. And this representation is called an adjacency list. So pretty much for every single node, for every single vertex, we keep track of, okay, what vertices are adjacent to it. In an undirected graph, the adjacent vertices are just like, for example, for one, the adjacent vertices are 2 and 4, and that's it. In a directed graph, it's a little bit different. It's adjacent to 2 and it's adjacent to 3, meaning that, okay, there's like an edge going from 1 to 2, and there's an edge going from 1 to 3. Okay, so let's go ahead and write the adjacency list for this top graph, for this directed graph right here, and for this undirected graph. Okay, so starting out with the directed graph, the adjacency list looks like this. So to 1, here are the adjacent nodes. 2 and 3 are adjacent. For 2, there are no nodes. There's no edges starting from 2. So therefore, its adjacency list is empty. Okay, so for 3, there's 1 which is next to it. So I can write it like this. And then for 4, there's an edge from 4 to 2, so I can write this. All right, so this is the adjacency list for this directed graph right here. Let me write the adjacency list for this undirected graph right here. Okay, so 1, there's an edge from 1 to 2 and 1 to 4. Yeah, I'm running out of space a little bit, but that's okay. 2, 1, 6. Okay, so this is the adjacency list representation of this graph right here. So as we can see, graphs might have like different kinds of representations, right? So the adjacency matrix representation is one, and the adjacency list representation is the other. Now, maybe as an exercise, you can figure out what the adjacency matrix for this graph would look like. And this matrix is a symmetric matrix. So for undirected graphs, the adjacency matrix is symmetric. So I'm not going to really talk about what that means. This is not a linear algebra course, but maybe you can Google it. It's nothing crazy. So for undirected graph, that means that the adjacency matrix is symmetric. All right. Now, there are really a lot of things which we could talk about graphs. But let's just we're going to be talking more about these things, let's say in a data structures and algorithms course, as you do more problem solving. But we just want to kind of get through a few basic concepts here. All right, so next thing. Now let's talk about this idea of connectedness. So I'll give you an example of a graph that's connected. I'm not going to label the nodes, but you'll see that this graph is connected. Okay, so why is this graph connected? Because from any 2 points on the graph, there is some way that I can get between them. So the graph is connected. Okay, so the word is connected. Okay, let's look at an example of a disconnected graph. Okay, so this is an example of a disconnected graph. As we can see, this component is connected, like this is like a connected graph, and this is like a connected graph, but there's no way in which we can like go from any vertex in this component to like any other vertex in this component. So this graph is what is said to be disconnected. Okay, so now let's talk about the next thing. We're going to talk about what a tree is. So there are a few definitions for trees. I am going to talk about a few of the definitions. So, all right, so here's what a tree is. Okay, so a tree is a connected graph which is also acyclic. Now let me talk about what acyclic is actually. So for example, this is actually a tree and so are these. These are actually trees as well. But what is, so like acyclic means that there is no cycle within the graph. So like what's a cycle? So for example, this is a cycle right here. Maybe I'll use a different color and see it better. This is a cycle right here. So we can see that there's like some path which we can take and we can basically make like a, like we can get back to the same point basically. All right, so basically that's a cycle. Maybe that's not really a super formal definition, but that's okay. We're just trying to get intuition right now. All right, so again, we can see, like, for example, why this one is a tree. This is connected and there are no cycles within it. And this itself is not a tree. It's actually what's called a forest, like a collection of trees. But as we can see, like this component right here is connected and there's no cycle within it. So it's a tree. And this component right here is like, yeah, is connected and there's no cycle. So here are two other definitions for trees, which are just equivalent. So by the way, like if you know that a graph is connected and it's acyclic, you know it's a tree. If you know you have a tree, it's a connected graph, which is acyclic. It goes both ways. Here are two other definitions. So two other definitions are the following. So let's say that, so I'll say it like this. So it's a graph with n vertices and n minus 1 edges, which is also acyclic. Okay, so that is, okay, that's another definition. Here is another definition. So a tree is a graph such that between any two vertices, there is a unique path. Okay, so for example, let's say that I'm trying to find the unique path between these two vertices, well, that path is only this path right here. Okay, there's like nothing I can take. Like, yeah, I can like go back. Like for example, I can go here, and then go like that. But then at that point, I'm just like repeating an edge. Okay, so I'm not in a path, I'm not allowed to like cross over the same edge twice. All right, so here are like some definitions for trees. Okay, now I'm going to talk about what a binary tree is. So a binary tree is a tree, and a binary tree has a root. Okay, and basically like you have different levels in your binary tree, and every single node, it can have up to 2 what are called children. Okay, so for example, I'll just draw a binary tree. Okay, so this is like a binary tree. So this node right here up top is called the root, R-O-O-T. Okay, and each node has like two children nodes. It has like a left child and then a right child. So this is like the left child node of this root. This is the right child node of this root. We would say that the root is the parent of these two nodes. This node right here, it has a left child and a right child. And this vertex, it only has a left child. Okay, so this is like an example of a binary tree. Okay. In future videos, we are going to talk about how to traverse through graphs in general and how to traverse through binary trees. Okay, so do be on the lookout for those, but hopefully this gives you a nice introduction to what graphs are. Thank you so much.